Let's talk about atomic spectra. You've probably seen these gas discharge tubes. Inside them, there's an elemental gas such as hydrogen or helium. And it'll be at low pressure. And then we'll attach a high voltage across the ends of the gas. And that's going to cause some ions to form. So you're going to have some electrons and some positive ions. Of course, the electrons are going to be attracted to the positive anode, and the positive ions are going to be attracted to the cathode here. Now, they've got some kinetic energy, and they're going to collide with some of the elemental gas atoms that are there. And that means there's going to be a transfer of energy. And these elemental gas atoms are going to get excited. They're going to get into an excited state. And then they lose that energy. And the way that they lose that energy is that light is emitted. So when we're talking about the emission spectrum from these elemental gases, that glow that's coming off the discharge tube, that's light energy produced as the atoms de-excite. And it turns out the light coming off each elemental gas is different, and the light characterizes that gas very well, and it has some special characteristics. And the special characteristic that it has is what we call discrete line spectra. If our discharge tube contains hydrogen, and you pass the light coming out of the discharge tube through a prism or through a diffraction grating so that the different wavelengths of light will separate, you'll get what's called a line spectra. And you'll notice here, the light coming out of the hydrogen discharge tube has 4 distinct lines. So there's 4 distinct wavelengths of light that are coming out of the hydrogen. And we don't get any wavelengths in between this 3rd wavelength and this 4th wavelength, etc. So there's just 4 distinct lines. Here's the spectral lines for helium. Helium seems to have about 6 distinct spectral lines, 6 distinct wavelengths. This last example here is what we call an absorption spectrum, whereas these first 2 were called emission spectrums. An absorption spectrum is formed when you take white light and you pass it through an elemental gas. So in this particular case, the white light is coming from the sun, and the gas is the atmosphere. And you'll notice here that once again there's some distinct lines here, places where that particular wavelength of light was absorbed by the atmosphere. So most of the light passed straight through the atmosphere, but some of it was absorbed by the atmosphere, some distinct wavelengths. Now, of course, physicists searched frantically for an explanation for these spectral lines. They needed a physical model to explain these spectral lines. And in the 1880s, a Swedish physicist by the name of Johann Rydberg came up with this formula right here. And it's able to predict the spectral lines of hydrogen. So it's simply 1 over 2 squared minus 1 over n squared, and n squared is simply an integer. It's got to be 3 or greater. R here is simply a constant, and then we'd plug in the different n values, and we'd get the different spectral wavelengths from the formula. Now, Rydberg comes up with this formula, but he doesn't have a physical explanation yet. He doesn't have a physical model. And it's going to be left to a famous Danish physicist to come up with a model that explains the spectral lines. By the way, you don't need to know this formula. I'm just presenting it for historical reasons. The Danish physicist was, of course, Niels Bohr. And in his model, there were only certain stable energy states for the atom, only certain allowable energy states of the atom. Or we could say that there was discrete energy states of the atom. Or we could say that the energy states were quantized. And he realized that that 2 that appears in Rydberg's formula as 1 over 2 squared, that was because in all the transitions that were producing visible light, they were transitions down to the 2nd energy level. So let's look a little more deeply into Bohr's model. The key idea in Bohr's model of the atom was quantized energy states. That is, there's only certain allowable energy states that the hydrogen atom can be in. These are the only stable states. And each time an electron made a transition from a higher to a lower energy level, that would produce a photon. And the photon energy would be equal to the difference in energy levels. So for instance, this here circle represents the 3rd energy level. So if there's a transition from that 3rd level down to the 2nd level, this red line is produced. because whenever that transition occurs, a red photon is produced. And the energy of that photon is equal to the difference in the third energy level and the second energy level. Transitions from 4 to 2 would produce this color of light, this wavelength of light. And 5 to 2 would produce this color, this wavelength of light, etc. Now it was only drops down to n equals 2 that produced visible light. And that's why there was a 2 in Rydberg's formula. However, as methods became available to detect ultraviolet light and infrared light, what was called the Lyman series was produced. The Lyman series was ultraviolet lights. There's a big energy gap between the second energy level and the first energy level. It's not depicted on this diagram, but there's a big energy gap there. And so whenever a drop is made down to the first energy level, more energetic photons are produced. And those photons will be in the ultraviolet region. And then transitions down to the level n equals 3 resulted in infrared light. This was called the Paschen series. So from n equals 1 to n equals 2, there's a big energy gap. But the energy gap is smaller when you go from n equals 2 to n equals 3. And then it's smaller again when you go to n equals 4, etc. So any drops down to n equals 1, there's always going to be a big energy difference, and that's going to produce a very energetic photon, which will be in the ultraviolet region. In fact, the energy levels in hydrogen go as this formula here. There's a negative sign because the electrons are trapped by the proton. That means they have negative energy. It would take work in order to separate the electron and the proton. This 13.6 EVs, that would be the ground state. E1 would be negative 13.6 electron volts. That would also be the ionization energy. In other words, it would take 13.6 electron volts of energy in order to knock one of those ground state electrons out of the atom. And then the subsequent energy levels vary as 1 over n squared. So n equals 1 is negative 13.6 eV. N equals 2 will be negative 13.6 divided by 2, it's the second energy level, all squared, which will come out to negative 3.4 EVs. And then the next energy level up, the third energy level, would be negative 13.6 divided by 3 squared, which comes out to about negative 1.5 EVs. So now we're going to be able to use this formula here, predict exactly what the wavelength is when a transition is made from n equals 4 to n equals 2, or for any of these different wavelengths here. Just using the idea that the photon energy, which would be h times f, or h times c over lambda, has to equal the difference between the two energy levels, which would be E initial minus E final. We can plug into that and work out the wavelength for a transition between any two energy levels in hydrogen. So let's see if we can work out the wavelength of light that would be produced from a transition from n equals 3 to n equals 2 in hydrogen. Pause the video now, try the question, come back for the answer. So hopefully you started out by saying the photon energy has to equal the difference in the two energy levels. So our higher energy is 3 minus our lower energy level, which is 2. Let's work out what those values are. E3 is negative 13.6 EVs divided by 3 squared. And that comes out to negative 1.5 EV. E2 would be equal to negative 13.6 EVs divided by 2 squared, and that should come out to negative 3.4 EVs. So our photon energy will be equal to negative 1.5 EVs minus negative 3.4 EVs. That comes out to a positive value of 1.9 electron volts. Now we have a formula for photon energy. Photon energy is equal to hf. Or because c is equal to f times lambda, that's just the universal wave equation, we can rewrite this as h times c divided by wavelength. Now we have to be a bit careful because this expression is generally given in joules. Unless, of course, we decide to write h in terms of eV seconds instead of joule seconds. This expression here is in electron volts. So what we're going to do is convert 1.9 electron volts into joules. And that means we're going to get that h times c, all of our wavelength, is going to be equal to 1.9 EVs times 1.6 times 10 to the minus 19 joules per eV. And the EVs will cancel out and we'll be left with joules on both sides of the equation. Then we can solve for lambda. It's going to equal Planck's constant, 6.63 times 10 to the minus 34 joule seconds, times the speed of light, 3 times 10 to the 8th, divided by 1.9 and 1.6 times 10 to the negative 19. Multiply that out and you should get an answer of 6.54 times 10 to the minus 7 meters, or you'd usually write that as 654 nanometers. A nanometer is 10 to the minus 9 meters. So you should get that wavelength for the 3-2 transition is 654 nanometers. Now, if you understand atomic energy levels, then nuclear energy levels are going to be a cinch because you do them exactly the same way. And that's because nuclear energy levels are quantized the same way that atomic energy levels are. So in the same way that an atom can get excited, a nucleus can get excited. But there's only discrete energy levels where it will get excited too. And it's going to work exactly the same way. We'll say that the energy of the photon that's emitted, this time it's going to be a gamma ray photon because it's going to be a more energetic photon. Photon energy is once again going to equal the difference in the energy levels. It's going to be that excited energy level state, the initial state, let's call that EI, minus the final energy state, that lower energy state that the nucleus drops to. So it's going to work in exactly the same way that atomic energy levels do. And now I have a few IB questions for you to try. Pause the video, try the question, come back for the answer. Hopefully you recognized that our photon coming in would cause a transition to a higher energy level. Whereas when there's a transition to a lower energy level, that's when a photon would be emitted. In this case, we're taking our photons and passing them through a low pressure vapor. And that means we're talking about absorption here. And that means the electron is going to go to a higher energy level. And that means the correct answer here is B. Another IB question, pause the video, read it over, try it out for yourself, come back for the answer. So hopefully you said the correct answer is A. And what you've got to remember here is that the photon energy varies inversely as the wavelength. So if we've got a long wavelength, that's a low energy photon. That means a small energy difference. If we've got a short wavelength, that's high energy. And that means a big energy difference. So we're looking for the maximum energy difference here, and that would be from 4 to 1. And we're looking for the minimum energy difference here, and that would be from 4 to 3. Because this gap is the smallest, and this gap is the largest. Another IB question, pause the video, read it over, come back for the answer. So it's an emission spectrum, so we're only considering the transitions from high energy to low energy to produce photons. So let's just count them up. We can go from here to here, here to here, and here to here, that's 3. We can drop from here to here, and from here to here, that's 4, 5, and then one more here makes 6. So the correct answer is D, 6. And that's all for today, folks. Thank you very much.